Okay, thank you. So it's Friday, it's the last day of the meeting. I'm sure we've got a lot of conference fatigue going on and people's minds are probably quite full. There's probably not a lot of room for any more additional information. But what I'd like to talk about today is something that hasn't been touched on much of this meeting, and that's basically where dark sector physics impacts the small-scale structure in the universe. I was going to say that it looks like our standard cosmological model works pretty good at the large scale, but after listening to Glenn's talk about anomalies in the CMB, I'm not so sure anymore. But what I want to get over to you guys today is that there is something happening with regards to small-scale structure in the universe that tells us that something's not quite right, and how we're going to try and challenge that kind of question. So, one of the problems about giving a talk on the last day, of course, is that all of the sort of introductory material has already been covered, and we've seen this kind of figure in one way or another over the last few days. And what we have, of course, is a nice standard cosmological model, which we've all grown to love, whereby we've got roughly 30% matter in the universe, roughly 70% some sort of dark energy component, which is causing the universe to accelerate. And of course, we have a whole range of cosmological probes that we've got that when we combine them all together, we get this very tight confidence limit on our standard cosmological model. So this looks very, very nice, and in fact, I work in cosmology, but I also work in other areas. This kind of picture really annoys my non-cosmological friends. This picture that we have where everything looks so good and so well defined to them is absolute evidence that we've gone horribly wrong somewhere and screwed something up, because nothing is this good in astronomy. Okay? So we feel pretty good about this. But there is a problem, and it's a problem that Offa touched upon, and a problem that I would like to also mention is that in terms of an observational point of view, if our universe is what we have here, which is 30% dark matter, if it is an Einstein cosmological constant, then in terms of observational cosmology, what we have is an exceedingly boring universe. Okay? What you're going to end up with is, it might be great for fundamental physics, understanding particle physics, fundamental fields, etc. But in terms of observing the universe, you have a very boring background against which to observe things. So the question is this model really as good as we think? Okay? Are there any issues that we need to worry about in terms of our observations of the universe in light of this cosmological model? And what I'd like to point out is that there are, and we should basically take what we've got here with a grain of salt and possibly think of other things that are going on in the dark sector that we might need to consider. So, the issues that make us scratch our heads a little bit, and when I say us, I don't mean just the people in this room, but also people who do not study cosmology. When I give talks on cosmology to my colleagues who work in astroseismology, etc., they do ask me questions which make you really scratch your head about if you really know what you're talking about. We've already heard about issues to do with the coincidence problem and also the fine-tuning problem when it comes to the size of the cosmological constant. Is it even a problem at all? If you ever give a public talk on cosmology, the blank looks you get when you tell people that we don't really understand what the dark sector of the universe is made of, often makes it look like we make a lot of this stuff up while we're down the pub, right? But we are struggling to understand what the dark sector of the universe is made of. The area which I think over the last 10 years has been a battleground essentially for the standard cosmological model is the small scale. And we had a nice talk by Ramil talking about the missing galaxy problem and also the too big to fail problem. And if you talk to some people, then these aren't really problems anymore, because you can wave your hand and say baryonic astrophysics will solve all of those problems. And in fact, for the small-scale issues that we have in cosmology, baryonic astrophysics has become the new magnetic field, right? It's a place where you hide your ignorance. Okay? I'm sure baryons can solve that problem. The one that I want to touch upon that has been grown over the last 5 to 10 years is that there is something fundamentally wrong with our understanding of dwarf galaxies. Not just the missing galaxy problem, not just the too big to fail, but this distribution of dwarf galaxies around larger galaxies. Now, I'm going to mention this briefly because I'm involved in this work and I think it's pretty cool. But we've known for roughly 20 years Now, if you look at the dwarf population around the Milky Way, dwarf galaxies just aren't randomly scattered around, but they tend to sit on a very well-defined plane. And as surveys have gotten deeper and people have found more and more dwarf galaxies, it seems like this very well-defined structure has become more and more significant. So we see that there is a plane in which the majority of dwarf galaxies sit, which are aligned with the pole of the Milky Way. Over the last 10 years, we've been collecting similar data for our nearest companion, which is the Andromeda Galaxy, and we're now able to basically map out the three-dimensional structure of roughly 30 dwarfs orbiting Andromeda. And you can go through the statistics, and it's a bit of a messy process, but if you look at the dwarfs, what you find is roughly half the population also sit on a very thin, well-defined plane. And not only are they spatially pretty coherent, they also have kinematic correlations. It looks like they're orbiting in the same sense. So the red galaxies here are the dwarf galaxies around Andromeda in the middle there. All the ones on the bottom are moving towards us, all the ones on the top are moving away. So it looks like there's coherent motion in the dwarf population. So this is pretty weird. Right? We have correlated dwarf orbits, and you don't get those correlations or anything remotely as strong as the correlations we see when you do a standard lambda CDM simulation. And earlier this year, we took the study a bit larger. We actually looked for correlated dwarf orbits in Sloan. And so we looked at galaxies with a redshift of 0.05. We had a relatively simple test. Again, looking at the velocities of dwarfs, whether or not they were correlated or uncorrelated around a major host. And what we find is that this signal that there are correlated motions in dwarf orbits actually holds out into at least the nearby universe out to redshift 0.05. Now, we get beaten by basically observational effects. It's very hard to see dwarf galaxies as you go out further and further, so we have a relatively small number of systems, but it looks like roughly 50% of systems that we can identify have these correlated dwarf orbits. And again, I'd like to stress that we do not see anything as correlated as this in any of our simulations of galaxy formation. So when you talk about this, again, depending upon the room who you're talking to, you can reach one of two conclusions. Both of them are slightly worrying. The one that we get a lot of is that we have these planes in the local group. Okay? We have planar orbits in the local group, but the local group is somehow special. Okay? And again, if you work in this game of doing cosmological simulations and dark matter in the local universe, if you find any evidence in support of lambda CDM in the local group, then that's great. The local group is a great test bed of cosmology. If you find any evidence against lambda CDM, then the local group is special. We should never use it to test cosmological models. Right? So this is the one that often gets touted, that we should not be using the local group as a test of cosmology, which really upsets a lot of people, especially those doing big galactic archaeology surveys, because that's precisely what all these new instruments are being designed to do, is test cosmology in the local group. The other conclusion is that there's something going on the small scale, right? On the scale of individual galaxy halos, whereby we have correlated motions which you do not expect from your standard lambda CDM universe. So again, since the missing dwarf satellite problem to today, it's the scale of individual halos that are posing the problems when it comes to basically agreement with regards to lambda CDM. So what is it that we want to do? Well, we want to understand the small scale universe, okay, and ask whether or not some of these anomalies that we are seeing can be explained by non-standard cosmological models. And by non-standard there, I mean just non-lambda CDM. And what we want to do is be able to play with the properties of dark matter and play with the properties of basically dark energy. And introduce things like interactions and decays in the dark sector, see what their imprint is on the small-scale universe. Now, of course, to do this, we have to do this in simulations, right? What we want to do is we want to take a cosmological volume, and have your mass distribution there, include your relevant physics, make sure you get your initial conditions right, and evolve that such that you get your linear evolution, but then you get your nonlinear evolution when your halos form, and ask what's going on inside those halos. And the key thing that we're trying to do is ensure that we observe our simulations in the way that an observer would observe the universe. We want to make sure that when we talk about potential observational properties, if we are able to tell one cosmological model from another, that we take into account the biases, the various biases, the various limitations you get in an observational survey. So we've started this program a few years ago. We've been running for a couple of years, and I'm just going to touch on a few results that we have at the moment, mainly to do with warm dark matter simulations and the interacting dark sector. We haven't gotten down to the scale of individual galaxies yet because it's computationally challenging, but we are getting down just below the scale of individual clusters. So just briefly mention the people involved. So we have a reasonably big international collaboration. Some of these people you may know. Christoph Beleko's name's been mentioned a few times. Chris Power, who's got a strong relationship with Cape Town as well. But the key people here are Harith Mahadi, who is a PhD student of mine back in Sydney, and Eduardo Carisi, who was a PhD student of Alexander Keen in Madrid and is now in Israel. So a cool bunch of people. So let's just start with the warm dark matter side of things. I won't go into the simulation in too much detail, right? But what we get is we take a standard volume of the universe, 150 megaparsecs cubed. We put mass in there. What we want to do is we want to generate two universes. One effectively a standard cold dark matter, lambda CDM universe. One where we have a warm dark matter component. Okay? So what we do for the warm dark matter in this particular case is we just do a simple truncation of the power spectrum. Okay? So we take some sort of mass limit and we equate that to an energy for our dark matter and just chop off the power spectrum. We include no thermal motions, and I'll come to that a little bit later. But what we do is we take our volumes, effectively take identical initial conditions, we evolve them, and we pull out the same clusters in a cold dark matter universe and a warm dark matter universe, such that we can do a comparison between the two. So we effectively pull out the clusters and then we re-simulate them at higher resolution. So the thing that we wanted to focus upon to start with was gravitational lensing. And we had a really nice talk by JP about why gravitational lensing is a powerful probe of dark matter. The question that we were looking at is the efficiency of a particular cluster of being a gravitational lens. And there's been studies over the last 10 years or so that have looked at cold dark matter clusters and compared them to observed clusters in the universe and found that the observed clusters tend to be more efficient, they're more able to produce giant arcs than our simulated clusters. And the question that we had was, if we mess around with the nature of dark matter, can we change the lensing efficiency? Now naively, you might think that if you go from cold dark matter to warm dark matter, you should make your lenses less efficient. What you've done, of course, is you've wiped out lots of small-scale structure, and so your lenses tend to be smoother, and so you've reduced the efficiency of your lensing. So the process is relatively straightforward. You just have here a couple of the clusters. You project your mass distribution. You then calculate the key lensing properties. So the colors in here, the blue are the caustics in the source plane, the green are the critical lines. You throw down sources, you reorient your cluster, you change your orientation over and over again, and you measure the efficiency for producing giant arcs. Okay? So as you can see from these pictures with cold dark matter, warm dark matter, we have clusters in this case here we have a set of merging clusters, there we have a single cluster, and you can calculate the lensing efficiency. And if you do that, you end up with this picture we've got on this side where we have, this is basically cross-sections of lensing for cold dark matter this way, that's cross-sections of lensing for warm dark matter that way. Okay? Straight line is a one-to-one comparison. And again, we've got 10 clusters, but we can reorient them many different ways. Okay? Because it's a projected mass distribution. And what you tend to see is that your warm dark matter clusters tend to be above that black line, which is where the cross-section would be equivalent. Which is sort of the opposite of what you would have naively expected. You would have naively expected that your warm dark matter clusters should be poorer lenses, and such that the point should sit lower rather than higher. So, why? Why are warm dark matter lenses stronger lenses? So what we did is we took our biggest cluster and we went in there. Remember, these clusters have still got structure in them, so they've still got halos within halos, and you can extract out the subhalos. And we did the same thing where we reoriented this cluster, and we asked what's the length and cross-section of these clusters with and without substructure in the warm dark matter cosmologies. And again, this is the picture we have. The red is the total cross-section to lens in, and the blue is the cross-section to lens in once you've extracted out the subhalos in the warm dark matter clusters. And you can see that this extra lensing that you're getting is due to the substructures that you get in your warm dark matter universe. So rather perversely, there's something going on in the warm dark matter universes whereby our substructures are giving us a stronger lensing signal than you get in the cold dark matter universe. So we scratched our head over this quite a lot, and it took a little bit of detective work. But what you find is that when you go back and you trace the evolution of the individual halos and ask how did these halos gain mass? Of course, in your cold dark matter universe, where your mass scales all the way down, everything grows by accretion of smaller halos, right? Little halos rain in, grow bigger and bigger and bigger. What you've got in the warm dark matter case is you've truncated your power spectrum. That you've still got the same amount of mass. That mass has to be somewhere, okay? And so it ends up being more smoothly distributed. And you get that your halos grow through a steady accretion of smooth matter. And what you get at the end of the day is that your halos end up being more massive and fluffier than the halos that you get in cold dark matter simulations. When you take those and you project them along the line of sight, that gives you more and more mass projected against the center, and you get that your overall lens efficiency goes up because even though you have less halos, they tend to be bigger and fluffier. And of course, this is a non-linear evolution. This is something that you wouldn't have predicted if you just, I mean, of course, hindsight is everything, right? After we went, well, of course, that's obviously how it happens, right? But beforehand, this is how we expected these halos to grow. So, quite clearly, there are nonlinear issues that go on even with these simple warm dark matter clusters that you need to take into account before you're going to make some sort of theoretical prediction for what somebody should see with regards to lensing. I should point out that even with this smooth accretion and boosting the lensing efficiency, that doesn't bring it up to the observed lensing efficiency that we see. So there's still an offset. Clearly what we've got to do is consider baryons, right? This is dark matter only. So the key thing here is what we found is that once you consider the nonlinear evolution, that you can affect the mass distribution in the cluster, right, by chopping off a mass scale around 10 to the 11. Right, so through nonlinear evolution, what you're doing is you're affecting the mass distribution on scales 1,000 times larger than where your cutoff is. So it's very important for us to ensure that we properly account for nonlinear evolution if we're going to make predictions for how the cluster is going to lens in this cosmology versus that cosmology. In fact, what we found is that this redistribution of mass happens on quite a large scale and starts to impact things such as the weak lensing signal on larger scales. And so you need to worry about where the mass is if you're going to talk about weak lensing in clusters as well. Okay? Now, a warning though. And this is not a new warning, this is a warning that everybody in the field already knows, is that we're adding physics to simulations, right? When what we want to do is add microphysics to cosmological simulations. And what we've got here, this is a cold dark matter universe, this is a warm dark matter universe, same universe, truncated power spectrum. And again, we've just evolved the simulation. And the fact that we have just truncated the power spectrum means that you start to create spurious halos. Here you can see 4 halos in a line nicely spaced out. And they're completely spurious. Okay? It's a result of the numerics. The fact that we've chopped off the power spectrum means you get peaks in the mass at regular intervals, and you end up creating these fake little halos. And what you do, if you don't like these, is you say, oh, I will now add thermal motions. We know that warm dark matter has a free streaming length of this, and so you add a velocity to your particles. But what you're doing is you're taking a free streaming length for a particle of the mass of half a keV, and you're adding a velocity to a particle which represents the dark matter, which has a mass of 10 to the 8th solar masses, so you give it a K. So we have a real problem that we need to worry about how we correctly add microphysics, because if that microphysics will have a nonlinear evolution all the way through our simulations, what we get at the end is we're going to be uncertain unless we really know that we added the microphysics correctly in the first place. So the other side is these interactive models, and these have had a very long history through a couple of PhDs in developing these models. I'm not going to talk about the specific model here because, of course, this is just one model of many that we could consider. But what you want to do is you want to take a standard lambda CDM universe, and you want to start asking, how can I modify that to include, a quintessence component, or an evolving quintessence component, or a quintessence component that interacts with dark matter, such that you get an energy flow between one component and the other. Okay, so this is just one model. We would like to consider others. It's computationally harder to do, right? Because there are a number of things that we need to worry about. Firstly is that for these simulations we need to include baryons as well, right? We can have flow of energy between various things. You end up getting quite complex couplings between the dark matter and dark energy components, so we want to put baryons in there. But we need to modify our cosmological code to ensure that we have the correct background evolution in terms of the Hubble expansion, correct evolution in terms of the various scalar fields and the force couplings, and we want to be able to vary the dark matter mass. If we're going to have energy coming out of the dark energy component into dark matter, we need to be able to change the mass of the particles. So it takes a bit of coding. You end up with a very blunted version of Gadget that's painful to run. Then you also need to stress on your initial conditions. You need to ensure that you do everything properly, that you go back, such your initial conditions is going to give you the correct gross properties of the universe today, such as sigma 8, etc. So this is all rather painful, and I'm rather glad to say that it was a PhD student's job rather than mine to worry about most of this, but we have a working code at the moment. So we just do the same as we did before. We run our simulations. We have our dark matter component. We have our gas component. And it's kind of hard to see by eye here, but that's our cold dark matter universe up there. This is one of the evolving and interactive ones. I said we don't really want to worry too much about particular models because we want to broaden the scope of models that we want to include. Once we had our first set of simulations, then what we want to do is start at the large scale and work our way downwards. As I said, our goal is to get to halos of individual galaxies. So, of course, the first thing you do when you have a cosmological volume, to measuring the halo mass function, etc., and finding that they tend to be very similar between simulations. You can measure the large-scale structure properties. So you can go through and you can identify regions which are voids and which regions clusters and sheets and filaments based upon the velocity tensor. And what you find is that on the large scale, essentially these simulations come out to be virtually the same. Which is what you'd expect, right? We wanted to go in and ensure the initial conditions give you things like sigma 8 are going to be the same today. So you would hope that the overall topological structure wouldn't be radically different. You do find slight differences where you get low density regions, the edges of voids, etc., but they're not too strong. When we get down into individual halos in terms of cluster halos, this is where we start to see differences. Okay? And again, it would be very hard beforehand to take your non-standard model and make a prediction for what you'd expect the gas to be doing inside a cluster, because you have your non-linear evolution. But we're starting to find that inside our cluster here, you get slightly different mass profiles, slightly in factor of 5 to 10%. But you also then get slightly different gas distributions. Okay? Now, gas distributions are nice because gas distributions are related to X-ray temperature distributions. And again, the differences are quite small, 5%, but we're looking at just how much you'd be able to tell one cluster in one cosmology from a cluster in another cosmology. But the differences, are relatively small at this kind of scale. Where we are at the moment, and this is work in progress, is what happens if you now look at the halos within halos. Right? So we're now getting down to look at individual galaxies within the clusters. And what we have here is the distribution of halos. Don't worry about the normalization, but the overall distribution looks roughly the same. But in these other panels, what we started to do is map out the shapes of the halos. So the halos tend to be triaxial, and the question is, which orientation do these halos have, and how are they orbiting within the cluster? And what we are starting to find is that at this level, we are starting to find a more pronounced difference between the clusters in the various cosmologies. Okay? So, we don't have an answer yet, but these kinematic profiles, or kinematic properties, I should say, might be a way for us to tell these different cosmological models apart. Okay? So, just to take away from that, right, we are seeing that in these interactive models that we have, there's one set of models that we have, that the large-scale structure of the universe looks pretty much the same, but we are starting to see differences inside cluster halos, which now makes us wonder what happens if we go down another level and ask what's going on inside individual galaxy halos. And that's the next plan, is to speed up the code, to push the resolution, and start to be able to resolve individual galaxies. So, what's next? Well, we still have this rather open question of which models should we consider. Okay? And after spending a week here, I now have even more models that I should be considering rather than less, right? So we need to think quite hard because there's a lot of computational time needed for each one, as well as getting the correct microphysics in there such that we get the correct evolution. So we're trying to work out what's the best set of models that we should be considering. The part that we need to turn on in our codes is the baryon astrophysics. Right, so far we've dealt with just adiabatic gas. We've turned off star formation and feedback AGN because that would just complicate things, but it complicates things in a way that we will need to consider when we talk about observing the universe. There's a whole bunch of potential astronomical probes, and we have various people working on these. The large-scale topological evolution is, this issue with the age of voids. Do voids evolve the same way in one model as opposed to the other? Correlated angular momentum. There are a number of telescope programs underway where people are measuring the rotations of galaxies and questions whether or not rotation is correlated on large scales. And others, right? And feedback into baryons. So we're hoping that we can tackle all of these into our various models. Okay? So I'll just put up my conclusions and just say that I think that our cosmological model, while good, is not perfect, and there are still anomalies that we need to address. We are trying to consider these non-standard processes, but it's not easy. But what we hope to do is hopefully develop new observational codes that will allow us to measure whether or not there's evolution and interaction in the dark sector. Thank you.
Dark sector. There you have this kinetic term with the phi, and then a potential with the phi, and then a reactive mass term m side by side. Now this m is a function of phi because this phi, this m, should be connected to some kind of equal-type potential. I mean equal-type couplings, because this is a reactive mass term. In phi, I see you have taken some exponential minus beta something. I mean, this part is not really clear because m phi should be this is a Dirac mass term, and this should come from the interaction with the scalar equal-type interaction.
So I should point out that this particular model that we've taken, this is I don't know about the Lagrangian. I know about how you implement it in the code though. Is a relatively standard model that's been used by us and another group. And I don't know what the answer to your question is, other than what we do here is this translates into force couplings between dark matter and the gas. Yeah, so it changes the coupling, so that's the way that we use it at the moment.
So you have talked about the spatial correlation with the orbit of dark galaxies as like one of the motivations, right?
Yes.
So does your WDM simulation actually account for, like, can you
No. No, WGM doesn't solve it. WGM just wipes out small-scale structure, but it doesn't put things on correlated orbits. But what we said, we think that the issues are in the small-scale universe. So you can solve the missing satellite problem with WGM, right? Which is part of that motivation for looking at WGM. We're not expecting every one of these models to provide a solution to all of the problems at the moment. We're just exploring the space.
Yes, a quick question.
Are you on my side?
No. But I'm talking about something that we didn't do together. It's about quantum matter, your quantum matter simulations. You're using a very low quantum matter particle mass, 0.5. Do you think that if you use, let's say a colder quantum matter like 3 or about 3 AD, you still see this difference in the frequency second?
That's on the to-do list. Yeah, we want that one model. The models that we took there were run by Chris Power a couple of years ago, and we just turned to look at the lens inside of it in the last year. Now we've got these lens results. We want to run a suite of them with different dark matter masses and see if these hold across the board.
Because it's something counterintuitive. Because I did myself also quantum matter simulation, but people have been and they didn't find any difference in the mass profile, in the density profiles of quantum matter cables. They fit very well in about the even if you chop off the spectrum as quantum matter, you still recover the same NFW. So you say that you get a fluffier.
You get fluffier halos. That's what happens. So thanks a lot to the organizer, first of all, for inviting me to give this talk. And so I come from Portsmouth, and let me start with credits. So this is the subject of this talk today. I want to talk about the work that I've been doing in Portsmouth with my colleague David Wans, in collaboration with two visiting students, Valentina Salatelli and Nashla Said from Rome, together with their supervisor in Rome, Alessandro Pacchiori, and the work has been published a couple of weeks ago at PRM. So outline, I want to mention a few things about the standard model of cosmology and alternatives and the problems, but we had a very good introduction by Jean-Philippe Poussin that helps my arguments. Then I will move into describing what is the interacting vacuum CDM scenario, and then consider a simple model for the interaction and what the results are, and then I will have some conclusion outlooks. So the standard cosmology model, as shown before, is in fact so standard now that this type of figure, you can see this is not coming from a recent Revit Weber. This is from a textbook for astronomy for biologists. So this has become so standard that is spread as the new way of thinking about cosmology.
So that's the flat lambda CDM, and this is based, as we know, on three main ingredients. First of all, we have the cosmological principle, and so we assume homogeneous and isotropic background models. And then on large scales, we model the universe with relativistic perturbations. These are important for the CMB and to compute the growth factor. And then, on small scales, we use Newtonian simulation. So on this base, we have this standard model of cosmology. Alternatives. We have heard this morning, and in fact, all this meeting is about, in a sense, also the alternative to lambda CDM. And the main one is still keep GR as your gravity theory, the cosmological principle, and then modify the dark sector, and we have many possibilities, and alternatives to modify gravity and still keep the cosmological principle. And another one, as we heard yesterday from Timothy Clifton, we can consider battery action problem. Then also, let me mention that phenomenologically, we need to simplify the description in few numbers for astronomers to work with, and we have standard parameterization at a constant W or W naught, and it's the first derivative of W. So in this talk, I will assume GR and the cosmological principle, linear perturbation only, no non-linearities, and basically what I'm going to present is the merging of three main ideas. One is the modification of standard lambda CDM only at late times, the interacting vacuum scenario, which is a phenomenological scenario, and instead of postulating a specific model for the interaction, we just parameterize the interaction and ask the data if we have interaction or not. But first of all, let me mention a few things that I've learned from previous work. I believe that it's important to study the models that don't work to see where they fail, and we learn something from that. And what I learned is that two main things. Don't mess with the early matter era, because you mess with the physics of the CMB, and these inevitably give you problems. And also, you want structure formation to be described by standard CDM. You don't want a Jeans scale that mess up your structure formation on small scales, so you want an effective speed of sound to equal to 0. So this is not new. What I'm saying, this is a paper by Sandvik et al. Here they were looking at a generalized challenging gas. You have an effective speed of sound, and basically, if this is positive, then you suppress structure formation on small scale. If this is just a parameter, so it can be negative. If you have a negative parameter, then you have a blowing up perturbations. I did something similar with a model where the assumption is that there is a constant effective speed sound, a unified dark matter, and again, the result is very similar. Extreme constraints on the parameters, and therefore effectively you come back to yeah. CMB. Yes, this is another model where we instead try to see if we start with a completely standard matter era, and then instead of having just a standard lambda CDM, we have a transition to a late time lambda CDM phase. Again, in general, you fail to fit the CMB. However, in another work a few years ago, we looked at a late time interaction in general within two very general fluids, and we just studied the background and just the late universe, and then compared this simple model with data. And in particular, we considered the case where we had the two coupled fluid are just some standard pressureless fluid described in CDM, and the vacuum W equal -1 and W 0. And then what comes out is, do we have a pointer here? Oh, sticker. is that comparing with supernova, data points are alineated on this line, which represents an interaction, in this case, which is just proportional to the energy of the vacuum. Okay? So this was some previous work that we learned something from. Okay, so let me now illustrate this vacuum scenario. So the idea here is to go back to basic. We just have a vacuum and CDM, like in land CDM. However, these two can interact. So this is a scenario investigated by David and collaborators in the last few years. Let me describe how this works. So we have a vacuum energy, and therefore the energy momentum tensor is just proportional to the metric. And if we look at the perfect fluid interpretation of this, indeed, like for lambda, you have that rho is equal to minus p, and this is what we call V. Okay? V is the energy density of this vacuum. However, this energy momentum tensor, therefore, just proportional to the metric, doesn't define a forward velocity. So no preferred forward velocity. So indeed, the simplest possible case for this vacuum is to be homogeneous, in which case, and homogeneous here I mean in the space-time sense, okay? If this is homogeneous, then this can only be a cosmological constant, okay? However, the vacuum can be inhomogeneous, in which case the inhomogeneity represented by the derivative, the gradient of the energy density, will be, of course, the source term in the conservation equation for the vacuum. Okay? And this is the energy flow for vector. So you can have an interaction, and these give you an inhomogeneous vacuum. Then, of course, through contracted Bianchi identities, you want the total conservation, and this implies that the energy momentum tensor of matter, which is just T here, also satisfies the conservation equation with the source term, which is just minus q nu. So for velocity, as I said, the vacuum itself doesn't define any preferred for velocity. In general, we have for a perfect fluid a preferred for velocity because it's just the eigenvector of the energy momentum tensor. Okay? So nothing like that for vacuum. So any for velocity is for an eigenvector for the energy momentum tensor of vacuum. So in a sense, all observers see the same vacuum, so there is no for velocity is undefined. However, a preferred direction is defined by the energy flow. Okay? And however, this means that this flow is irrotational. Because, as we said before, Q nu becomes to be defined as just the gradient of V. So, if you spatialize this in a Robertson-Walker cosmology, then of course everything is just function of time, and then you can construct basically any interaction starting from the V you want. Let me also mention that one can, starting from a generic dark energy cosmology, you can decompose it into an equivalent vacuum plus fluid for the background. Okay? So you can do this for the background, and then you have a two equivalent interpretation of the background. However, these two descriptions will be different at the level of perturbation. Okay? And indeed, in general, for perturbation, one needs to specify the four velocity, the four vector of the energy flow. So in homogeneous perturbation, standard perturbation theory, in general, rho is perturbed together with the vacuum, and importantly, both have a matter-free momentum flow. Okay, so you need a physical covariant interaction to determine the energy momentum transfer for vector. So saying, that's bottom line, the same Robertson-Walker cosmologies may have different perturbations, depending on what you assume for the full vector. So in general, then of course you have your perturbed equation of motion, the energy conservation and the momentum conservation. And the vanishing vacuum momentum requires vacuum pressure gradient to be balanced by a force on vacuum. So here is a sketch, Robertson-Walker cosmology with this standard slicing, homogeneous slicing, and then you perturb, and we use comoving orthogonal coordinates, orthogonal to the forward velocity of the matter, which is the only one in the game. And then, if you overimpose on these the slicing, which is orthogonal to the energy flow, then this means that on these red slices, the vacuum is homogeneous there. It's spatially homogeneous, of course, because Q, again, Q mu is a four vector, which is the gradient, the four-dimensional gradient of V. Then, by construction, on these slices, the vacuum would be homogeneous. Okay, so out of all possible models, therefore, we concentrate on the simplest possible one. Let me stress again that this is a phenomenological model, and eventually, I'm going to show you, we want to compare with observations and see what the data say, right? So we want just to construct the simplest possible case, and the simplest possible assumption that we can make is what we call the geodesic model, where the forward velocity of the energy flow is just proportional to the forward velocity of the matter. Okay? In this case, then, clearly everything, so the matter, therefore, remains geodesic, and in addition, this means that these red arrows are aligned with the yellow arrow. Okay? So therefore, in the comoving orthogonal coordinates of the matter, defined by the matter flow, the vacuum will be spatially homogeneous. And this is very convenient because it simplifies the equation in particular. When you plug in your equation into CAMP, the synchronous gauge will be very easy to implement, because then the vacuum is homogeneous. So essentially, the cold dark matter is perturbed in the same way as it is in lambda CDM, except that the background is evolving. Only in this special case, but it's very, very useful. Okay? The vacuum is homogeneous in common orthogonal coordinates, and there is no moment to exchange it with our matter frame. So matter follows geodesics. That is very important. This results in having a zero effective speed of sound, which means that therefore cold dark matter can indeed cluster as in lambda CDM with no Jeans scales. And because of this assumption, however, let me point out that this is a non-adiabatic model. Okay? So there are kinds of verifications. One drawback of this assumption, then, because U then is proportional to Q, is that the full velocity of matter becomes irrotational. This is not important for our simple linear perturbation model. So now, what we want to do now is to ask the data if we have an interaction or not. Okay? And we want to do this, as you have seen, so far I just described a generic interaction, except that I now consider a subcase where this interaction for vector Q mu is proportional to the forward velocity, and we have the geodesic case. So what we want to do now is to use a simple parameterization for this interaction, and then see what we can learn from the data. And we do this dividing the data into redshift bins, and then we want to see if an interaction is present or is excluded. And then, after I do this using particulars, you will see 4 beans. I will reduce to a simplest possible case of interaction in one single bean and compare with lambda CDM. So that's the interaction again, and so we divide with this. So ideally, we would like to have as many beans as possible to describe a continuous variation. In practice, what we do is to divide all the data that we use in 4 beans, which are listed here. And the idea also is that we choose the beans so that basically in each bean only one data set is important. Okay? So the largest, so the Q1 is the parameter of the interaction in the bean at largest redshift, and there is only the CMB that counts. No other data are there. Then there is an intermediate large redshift bean where what are important are the high redshift supernova, and then closer to us a bean where the important data are the redshift space distortion data, and that's really the key point, as you are going to see. So use large-scale structure information, okay, cluster information. Finally, at the lower redshift, we use low redshift supernova. Okay, so this is a sketch of the beans, just schematic. We first do an analysis in 4 beans, and then we just assume that there is no interaction at all in the first 2 beans and 1 interaction in the late bean. And let me emphasize again, here we are using, that's the parameterization we use for our interaction. We say that is proportional to a dimensionless parameter Q through H and B only. Okay? So that's the same interaction that I shown you before, where I just use supernova. Okay? So under that suggestion, this seems a good starting point. So here are the results, and the black lines here are lines with Planck only. The pink line are Planck plus supernova, and then the purple line are Planck plus redshift space distortion. So what you can see is that basically when we don't, supernova and don't change much the results from Planck. Yeah? Planck has a very strong influence, and then these are then when we add the redshift space distortion, instead we have a very strong effect, which basically works by breaking the degeneracy that there is between omega matter and this extra parameter, the interaction strength. Okay. And in particular, what you can see is that at the larger redshift beans, the first 2 here, Q1 and Q2, the 0 case, so let me emphasize this again, that for Q equal to 0, we go back to lambda CDM. Okay? So, the 2 larger redshift beans, high redshift, yeah, a 0 interaction is not excluded at all, but then when we look at the bean where redshift space distortion data are, clearly things change dramatically, and similarly in this bean. Okay? So as I said, the effect is mainly driven by the breaking the degeneracy. Okay, let me skip this. So here are the results. So a null interaction, when we consider the 4 beans, is excluded at 99% confidence level in bean 3 and 95% confidence level in bean 4. Okay? So then what we do next is to say, right, this is still a model which has 4 extra parameters with respect to lambda CDM. Okay? So because later I want to play the game of model comparison, 4 extra parameters a lot. Let's see if we can simplify the model even more. Let's just make a very simple assumption, which was back in this sketch, yeah, where we say, right, no interaction at all in the first bins, and then interaction in the last two bins, a single one parameter for the last two bins. Okay, and when we do this again, we find that we have again a 99% confidence level of excluding the zero interaction. Of course, this depends on the fact that we have fixed the initial redshift at which the interaction starts. Okay, so we try to change that, and this doesn't change the fit much. So here are just a comparison of our single one parameter parameterization with the interaction and the redshift space distortion data, comparing with the lambda CDM, which has the same best fit values that we obtain here for all other parameters and zero interaction. Okay? So here is indeed the effect of change in Z, initial Z. So basically there is a degeneracy with the initial redshift of the interaction, but things don't change much with respect to the 0.9 value. So one thing to mention here is that this model alleviates the tension, for instance, between H naught as coming from Planck and Hubble space distortion. And indeed, tensions between CMB and large-scale structure have been pointed out before. So indeed, that's actually how this simple parameterization of an interaction works. Okay? So here is a lambda CDM, and you can see indeed Planck only and Planck plus redshift space distortion, great tension with these two. And here, for comparison, we also consider the case of massive neutrinos. So in all these models, we do make a standard assumption, I'll come back to that in a moment, about massive neutrinos fixing the value of the sum of the masses. But one can actually consider this sum as an extra parameter and let y, and it is we recovered previously known result that these alleviate the tension at B, but our interacting model alleviate this tension even better. So, as I said, yes, that's the value we used for the neutrinos of keeping fixed, but we also looked at varying the sum of the masses, and we found that that's oh, sorry, this is 0.50 division. And then both of these models, the interacting vacuum and the varying neutrino masses, are single one parameter nested extension of lambda CDM, and so a Bayesian comparison can be done easily, and that's what we did. And of course, this is a game that one should play with care. Okay? Of course, this is an oversimplified model where, in particular, we fix the initial redshift. Okay? So we compared our model against lambda CDM, and also we compared the neutrino model. Okay? So this is the red dotted line is the neutrino model, and this is our best fit with the zeta in at 0.9 for just to see what happens changing the initial redshift. We computed 3 cases. And also, we plotted these against, here is the range assumed for the brighter. Okay? So of course, then the evidence decreases when you increase the range for the brighter. But I think the best thing that we can get out of this plot is that whatever you make in your assumption, this model performs always better than the neutrino. So, outlook. So this essentially, for the moment, is a scenario, I would say, in search of a model, because we don't have a specific model for the interaction. Rather, here we just made a very simple assumption in which we parameterize this interaction. That's the way I like to describe this. Okay? Could this be a simplified model or a more general interacting dark energy? And then, of course, if you have interacting vacuum, how these interact? So there are some questions to understand there. And of course, as I emphasized, this was just using linear perturbation theory and data where this applies. But then we need to extend the model to nonlinear scales, small scales, and look at what we can do with embodied simulations. And I'm also interested, of course, in considering nonlinear relativistic effects in these modified scenarios. Because as we know, in lambda CDM, all relativistic effects are typically small, because it's lambda CDM is like conspiring to have everything as Newtonian as possible. Once you break that, you may have bigger effects. And then, of course, the results I've shown are very strong. These are based on the current data, so we need new data and a new analysis. In summary, so vacuum energy is the simple explanation for acceleration. We don't have any extra degrees of freedom in this model. It's just standard vacuum, except that it's interactive. And the inhomogeneous vacuum implies an energy momentum transfer. And at the background level, any dark energy model can be rephrased as an interacting vacuum, but then you will have different perturbations. The model-independent constraint we used show that indeed there is a very strong suggestion for to exclude the null interaction at 99% confidence level. So does it mean that we start to see evidence for wave-time interaction? You should see. Thank you. Let me conclude with saying that we always welcome hard-working visiting PhD students. We have a history of visiting students from South Africa, and please come and visit us. Yes. Ron.
You said at the end, no extra degrees of freedom, that's quite right. With this interaction, holds quite a substantial
Well, I guess I mean degree of freedom, like we don't have a scalar field or something that requires extra dynamics, right? You do need, of course, some assumption about that.
But I think the actual interaction contains a lot of devils in the detail. So
sure.
you cannot actually parameterize the interaction in general. You have to choose an interaction and then you parameterize. So for example, your interaction is proportional to vacuum energy. You have a sign, and I note your Q parameter goes across negative and positive. The one sign corresponds to an energy transfer from dark matter to dark energy, and the other reverse.
Sure.
Physically, one would have to try and understand what those two things mean. Can you actually physically, or either of them ruled out by entropy consideration?
Absolutely.
Yes. Ways to go on. But the last point was, if you just switch this interaction on, that's also not physical. You have to be, unless you can phrase it in the sense that the interaction is negligible until reaction point 9. Because if it's a fundamental quantity like the vacuum and dark matter, the interaction that you postulate exists from.
Sure, but this is, as I said, this is, I call it scenario in search of a model, right? And what I use to compare with data, I don't call it a model, I call it a parameterization. And of this beam analysis is very standard, it's not we have done something
All I'm saying
new.
is the parameterization is already dependent on.
Well, of course, it will be very nice that someone else does a similar analysis using a different parameterization. The entire idea here is that the result shouldn't depend on the assumption made. That's our plan.
I'll claim it depends on the interaction model, on that full vector that you
Jean-Philippe.
Just to be sure I understand, your interaction is just between this vacuum and dark matter.
Yes.
So if you have that, it means that equivalence principle between dark matter secure and standard matter is violated. You should get like an extreme bias. I mean, at least you have a linear bias in this thing. So how do you control the bias? And how are you sure that?
Good questions. But in this game, I think it is not very important. What I mean is that comparing with this data and just using linear perturbation theory. Yes, what you're saying is that, for instance, I could have the same. The magnitude should interact with everything, especially violence, right?
Yeah, even in a cluster or in a galaxy, like a spiral galaxy, you have the head of dark matter, you have normal star. They don't feel the same gravitational, I mean, the same effect. I mean, there is an extra of the dark matter that you have on the star. Can you try to compare this?
Needs to be done. One thing I didn't mention, of course, is that this was a short analysis, and we have a bigger work in progress.
I mean, I know, for example, that people have looked at, whether black holes sit at the center of dark matter halos, and if there's a force on the dark matter halos, not on the black holes, you get offsets and little triangles.